Just don't want to be annoying to you.
Hello. All right. Welcome to Data Mining Times Security. My name is Rich Seymour, and I've been given the opportunity to talk to you folks. Thanks to Clarence. I work at Endgame. I think Endgame is probably paying for this. They're the best. Endgame is the best. I have a thing to say about us. Our CTO recently said that NSA DNA is our company's soap in. I think is what he said. But don't quote me on that. Endgame was founded in 2008 and has provided a variety of cybersecurity solutions to the federal government. We are in the process of transitioning those capabilities to support the HUD mission within private industry, with a focus on protecting critical infrastructure. We are roughly 140 employees, including a diverse range of scientists and engineers, growing year over year across our 4 offices, which are in this beautiful city of San Francisco, San Antonio, Texas, Melbourne, Florida, and Arlington, Virginia, which is where I work. Tonight, we're going to talk, some of us from R&D are going to talk about some of the things that are going on. All right, so without further ado, I'm going to talk about experimenting. Daniel and I are going to talk about experimenting with user attribution based on bash history. So I don't know how we're going to do this next slide. Here, you talk about yourself. This is Daniel.
Hey, how's it going? So I'm Daniel Brent. I'm a data scientist at Endgame. Come from Georgia Tech background. I like to say I played Battleship professionally in my previous job. But technically, it's mission level modeling and simulation. And what I focus on mostly at Endgame is unsupervised process and user-based anomaly detection. So trying to find the attack or the attacker without knowing what you're exactly looking for.
Yep. And I'm Rich Seymour. I studied material science and high-performance computing in a past life, and now I work at Endgame doing all sorts of things. And I'm on Twitter. Daniel's not on Twitter, so give him trouble for that, but it's R. Seymour. Then these are your slides, and we'll switch back.
Okay, that's good. We're sharing. That's good. So what we're doing in this first presentation, and even in the later presentations, is talking about experimentation. So the parts of that we're going to focus on, if you've done engineering school at all, you'll probably recognize a lot of this. It's the engineering method. It's know what your problem are, your goals, your constraints, what your resources are, and then do some design, the creative process, brainstorm, and figure out what you can do. Then try it out. You want to try it out on a small scale, and then iterate where to mess up, and then see if we can actually put it into production. Either as a full-fledged system or a module or a tool that you use. So for knowing your problem, what we're going to talk about today is trying to identify users, either positively identifying them or negatively identifying them. So is this user, or is this user not this user? And I think we'll talk about that a little bit more, about which one is easier, which one's more useful. But based on their interaction behavior. So we're going to be able to look at bash history, process execution history, a lot of this sort of stuff. At Endgame, we have a system that has a collector on those machines, so we get a lot of this information. We basically just ask it whatever we want to do. So we can get bash history, we can get all clock set events that happen, so system level. And then we have some constraints about how we want to actually apply this. So one of those is it's always on. We want to have sort of security as a service. So we want this to be monitoring constantly, so we can actually identify threats all the time. We have to be careful about creating too many false positives or too many alerts of just anomalies, because if you get hundreds of anomalies or alerts or whatever you want to call it a day, you're not going to pay as much attention to them. That's called alert fatigue. And we also have lots of users. So if you're looking at a system like this, you have this problem of checking anything against several users. There's an experimental design problem there where you're going to get false positives all over the place. So that's something to keep in mind. And now we're going to transition to Rich, which we just inserted the slides right after this house.
Okay, so we'll go back to Daniel in a second, but first I'm going to be mildly depressing. So how many of you guys have used a command prompt today? Some sort of CLI. How many people use PowerShell today? No, that's not that good. What about cmd.exe? About command.com? But that's fine. So I'm not going to be talking about the Windows-based stuff. We're basically just going to be talking about Unix stuff. So most people know the shell as the outer part of the kernel conceptually, but technically the problem is that it's really not. Like, you can have all the shell history you want, and as soon as someone installs GUI or any number of services, they're going to be running without ever touching the shell. So first, like, just knowing shell history doesn't give you a lot of information. It's a fact. It's a sad fact, but it's a fact. So this is where it's going to get a bit historical, and I have a photo here. How many people were using computers in 1999? Great. Computers. This is me using a computer circa 1999. Anyone, the ML folks will love that in the blackboard it says artificial neural approaches. Unfortunately, this lab was a solid waste recycling lab, which could have used artificial neural approaches. People are doing that now. There was a vulnerability at CE 1999. I tried to look it up after the fact, 15, 16 years later. It was one of those like really good ones. It gave you remote root essentially instantly off-the-shelf script kiddie stuff. And it was installed by default on Red Hat Linux 6, not Enterprise Linux, but Red Hat Linux 6, like the original good stuff. I'm pretty sure this is the vulnerability that was used. And the guy across the hall was working on radar stuff. He gave all his grad students a nice, I don't know if it was a Pentagon at the time, but a 46, but he had 5 of them, and they were all rooted remotely because they all had their own IPv4 address. So we tried to fix it. I don't know if OpenSSH was actually a good option back then because you couldn't RPM install it, but the first thing you learn is that there's no history. You can delete shell history very easily. It's like you look at people hacking machines, whether it's on Mr. Robot or anything. There are ways to avoid history. Like, what's the easiest way for you to accidentally avoid saving something? Any guesses?
What's the question?
The easiest way for you personally to accidentally avoid saving something is, yeah, out of space, which happens all the time, right? If you might be copying stuff off the internet, never know who's next to space. That's irrelevant. So what back when OpenSSH had them on. So what is history good for? Well, let's go into how you look at your own history. This is a simple command, and when we post the slides, you can copy and paste this into your shell. And this is basically off Stack Overflow. How can I get all the different commands that I run first? And when you throw it into some heavy-duty data science tool, you'll see a graph like this, where you probably can't read that. I can't read it. I zoomed in a little bit. And then I did this. So the first one is git, which is interesting. That wasn't what I thought was my most used command. Vim cd fig. So this is just the command, and it was unique by command line, if that makes sense. But the issue is that if you're using ZSH like I am, you're actually not storing commands raw history, right? You're compressing them. So this is what the graph really looks like is I've deduped my entire history. So all the LSs are just one entry. So my personal history is not really a good reflection of what I do on command line. Unfortunately, right? It'd be nice to know. So what is history good for at all? Like, why am I even talking about it? And there's actually one time when you get really nice, clean history with, in the security space, at least. One time that I can think of, which is honeypots, right? So if you have a nice Cowrie or Hippo honeypot active with a nice, easy to guess password, someone can SSH in, you get to see exactly what they do, and it will save like down to the keystroke, which is nice. And you'll get a graph like this, and that's our data. Thank you, Andrew. And over here on the left is a command that begins with W. And it's not a crime to use W, but it is very common for people who crack into your system. So how would you ever put this into use? Let's say you had an active honeypot and you had a machine that was 20 years old and you have to keep this random password on it because that's just the way it is, and you know that some bad guy is going to guess that 6-character password. Well, you could compare a user history from a honeypot to your user history on the machine and maybe blacklist something or some magical thing. But the issue is, how would you ever exfil your own employees' data off that machine, their history? And I think that's a dangerous question, right? Because what you look at, this is, I mean, I'm kind of stealing that concept, but if you're in India versus in the US versus in Finland, what an IP address is and whether that's PII is completely different. Here, it's like profitable information that you can sell to your advertisers. And in Finland, it's personally identifiable information that you need to avoid. And in India and China, different rules apply. Here, it's actually state-based. So here's an option with a very small URL from, I don't want to mispronounce his name, but he's at Docker now. He was at Square before, I think. Diogo? Diogo. Extremely intelligent person who used this to look at user passwords. So you can hash somebody's password in this kind of neat way and find out what your most used passwords are by storing them, the hashed versions, and saying, well, people who've been reusing this password don't use it. And I guess you could do that. But the problem is that when you try to take that history and say, well, this was honeypot history, this is definitely hacker, how do I then talk and say that that's definitely a hacker from whatever? This is the 1977 manual on microscopy of hair. Has anyone ever done with the hair under a microscope or a microfiche? People that have hair. It's an interesting issue with the attribution with the FBI because they had it basically doesn't work. Unless you really, really follow that manual and follow the caveats, you'll end up in deep trouble. Like this is like, you know, I don't know. People use social justice worker as a bad thing, but when you have a 90% failure rate in, you know, like convictable evidence, that's probably something we should fix. So they are kind of retroactively trying to execute the folks that got executed. So don't do that. But what can you do with shell history? Like we keep asking this question. And the problem with shells is that they're so old, right? Like how old is ZSH? Any guesses? How old does it feel, that shell? It's 25 years old. Like it's older than people in this room, for sure. And it's like, that's new tech. There's Fish, which is 10 years old, which can kind of help you use your computer a little bit. But Bash and SH and KSH, those go back to the history of Unix, basically. And they're not that helpful. So what can we do, I think, in the future is prevent users from doing stupid things. That would be really nice. If you're about to delete something, that was probably one of those innovations in Red Hat 5 or 6 was they were like, you're going to need to rm-f if you really want to delete something. And they threw an alias in there that probably saved petabytes of data when you think about it, like over the years of like, are you sure you want to do this? Those sorts of little things are important. And also, insider threats are crazy. Like, if people have human errors, like errors in judgment, where they want to do something bad, that's fine, that happens. But most of the things that really happen to hurt us as companies or as people are just accidents. You delete that thing you really want, you just lose it. And having your shell help you with that would be really, really nice. Is anyone familiar with Bro? It was like a half, well, not Bro, the network security monitor. Yeah, everybody should be familiar with Bro, the network security monitor. It's really useful. Bro pages were like a failed attempt at adding examples to man pages. But it was like sort of like a half-assed project that came and went very quickly. But integrating that stuff into your shell would be nice, like that XKCD comment about, you know, write a valid tar command to disarm this bomb, type of thing, which is hard, right? And maybe some sort of Clippy-esque thing. People are often scared about their source code getting exposed, right? How many people outside of the defense industry should really be scared about this? I don't know. Like recently someone was convicted on 500 megabytes of information in Canada. I don't know. It's interesting to think how long does it take to get 5 megabytes or 500 megabytes out of the computer. Anyway, just some things to think about. I think I covered most things. Now Daniel's going to talk about what you can do with batch history data.
Okay, cool. So based on a little bit of that, a little bit of background, say you do have batch history, say you are at a or you have it recovered. We're going to go through an example of one of the experiments that we went over to try to do some sort of user attribution. Example history, you can do it either by the exe only, so you're looking at like sudo, cd, ls, all that sort of stuff, or the full command line. Those, if you're doing those and putting them into a matrix or putting them into a unique sort of system, the exe only is going to be a much smaller set of data versus full command line. So that's sort of where the experiment lies, trying out both of those things which works better. And we wanted to plan it out a little bit. I sent an email out to all the engineering and research org in our company and asked them to send me their history. Gave them the command, showed them what my history looked like, just to make sure they were okay with it. And I got like 11 sources back out of 140 person company. So people don't really want to share it that much. What was that? Not many, but I did clean out a few things. And also as a tip, if anybody does do a lot of command line interface and they don't always type the right command for permissions, you can add this alias, plug equals sudo history p bang bang, and that'll be your last command as sudo, as a super user. So it's pretty useful actually. For me at least. So one of the first starts is brainstorm a lot of ideas. You can do association rule mining, end-to-end creation, and clustering, Markov chains. So this is actually like one of the more fun parts of it. Figure out what you think you might do. And then you want to plan ahead to figure out which of these are actually feasible in the long term. So if I have to do something where I have to have like the entire user history of time, every time I need to recalculate the model, that's probably not going to be great. So plan that ahead, but you can't really go down like a rabbit hole and like plan out the entire thing before trying to see if that works. So I think every data mining or data science has to have a quote by entry. So that's ours for this one. So do step 1, 2, and 3, and then figure out if you need to do step 4. So maybe plan ahead before you can actually not do step So we decided to go down the route of trying it out with a Markov chain. We'll do a quick overview of what a Markov chain is, what a Markov process is. So if you have a sequence of items that come in a list, it's a probability model where the chance of the next item in the sequence is based only on the previous item in the sequence. So for an example, if you were monitoring the weather, this is the classic textbook example in 90% of the probability textbooks that you'll see. If you see one day it was sunny, one day it was sunny, one day it was cloudy, sunny, cloudy, rainy, you could figure out the probability of transitioning from sunny to sunny, sunny to cloudy, sunny to rainy, etc., all the way down the way. And then once you have this model built out, you can calculate if you have a new sequence, what's the actual probability of that sequence happening. Obviously, you need to keep the caveat in mind that as long as you keep adding items to that test sequence, the probability is going to quickly approach zero because you're multiplying by something less than 1. So that's just a little caveat for some later graphs. But we can also take this and put it into a representation that works much better with computers. So putting this into a matrix, a transition probability matrix, this is the exact same data as the previous slide. But this is saying, 60% chance to go sunny, 3% sunny, cloudy, 1% sunny, rainy, etc. And we can do this with our history as well. So we wrote a little bit of code to try out this experiment and figured, and you can see some things that make a lot of sense. So like Git has an 80% chance of transitioning into Git because you do Git add, you do Git commit, then you do Git push. And then you keep on going through this. So this is just like a small sample, a couple of items out of the matrix pulled out. But this is how you could actually represent it. This, as we're looking forward, this is not an efficient way to represent data on like the 500 by 500 matrix. So keep that in mind because you need to do a spark test. So if you do have a sequence of commands that you want to test against one of these matrices that you've built up now, you can test that. So say we have this sequence of commands, sudo or su sudo them lscd ls whatever. You can calculate or you can look up in your matrix the probability of transitioning from one state to another, from one state to another, from one state to another, and then multiply those all together and you get the final probability of that exact sequence. Okay, so that's the basis for it. We did this with some batch samples. We got a bunch of samples from a hosting provider and then anonymized a bunch of stuff on them. And then took any of the samples that had 300 items in the sequence. So we had 68 samples to choose from. And we created models with 90% of the data for each of those users. We left 10% out for testing. So like a 4 man's cross allocation. So once we did that, the items on the left, and I know you can't see them, but even at good resolution, you can't see them, so it's okay. But the items on the left, the index over here, those are all the different users, different potential users. And so each one represents like one person that had an account with this person or with this service provider. They would log in, they would do stuff on their box, whatever. We created a model for each of those users based on 90% of their data. And then this graph itself represents testing a sample from one of those users against every other user. So you can see out here, this one was actually the sample that we tested, and this is all on log scale. These are actually 10 to the negative something numbers based on that. Multiply something by a number less than 1 like 50 times, then you get the small number. So you can see like this one made a lot of sense. It looked like it was that user. But we also had the issue of, since we're testing against so many items, you have the problem of you can't always positively identify a user based on that, because if you have like a 5% confidence interval of your test, and you test it over 20 times, you're likely to get a false positive that actually looks better than your true positive. That's just like math. But you can say like it's in the top 5%, top 10% or something, and it's a decently accurate thing. We got 27% accuracy out of this, and it's simple, not even 97% accuracy that the sample that we were testing matched, or the model that we created for that sample matched within the top 5 of those models. And most of the time it was actually, so we only had one that and this was with the batch history. Since we have process execution history, we decided to try that again. Like Rich was saying, like batch history doesn't show the entire story. Process execution shows everything that happened, even for like data users. So root user does one thing, your Docker container is another user that does one thing, all that sort of stuff. So it was a very similar idea. We have execs in the full command line. You can sort of create a user by doing host and UID and those ideas. Because you can't guarantee that UID, as shown in the system, is the same in one machine to another. So these actually represent several different machines that we have monitors on. So we have similar results, and we just for these top, we all came from the same machine, different users on that machine. Next 3 years, different machine, different machine, different machine. But you can start to see a pattern between a lot of these. And they actually match the clustering that we do another way. So you can see the top 3 machines all serve the same purpose, and they have the same users that do the same thing. And the bottom machines all serve the same purpose. They have the same users that do the same thing. So there's a little bit of validation in the idea, and also identifying it from a completely sideways manner going into it. Since we previously had identified these based on like all the installed packages, for example. And then the final step of like after you do your experiment, say you validate it, you want to actually do it in production, try it out. There are a lot of concerns you have to figure out. One problem is we have 97% accuracy on that. That's not good enough for security. If you have 1,000 users that you're monitoring, 10,000 machines that you're monitoring, if you have 3% error, you're going to have 300 false alerts or 300 missed alerts, depending on which way you're looking at it. So usually the way forward on that is combined with other indicators and have like a sort of amalgam of approaches that all work together. There's an issue of long-term maintenance. This is fun. I can do this in an iPod notebook. But you want to put this into production, you have to be able to APOP that. You have to be able to do updates. You have to keep on doing that, like ad infinitum. So there are a couple other ways you can mess with that. You can do batch updates and stream updates. You can keep on the data and you can slide it in there. A lot of that depends on how much storage this data actually represents. A lot of times it's really nice to represent it into a very compact way. You just keep that, update that, and then work forward with sliding windows after that. So storage and accessibility. If you're running this against every single you have, and you have to pull up a model every time just because you're doing functional stuff, that doesn't always make a lot of sense because you're going to do all that overhead. So you have to keep all those in mind when you're trying to build something at scale. And it's always really nice for when you're building this code, when you're building these repos, it's really nice for engineers. I can't tell you how far it gets you to actually submit your code and put in tests and implementation examples for people that are actually going to implement what you're going to do. It makes their life easier, it makes your life easier if they don't just go to you all the time. So that's both of that. And that's basically just the example of like what we had of an experiment that we tried real quick, see if we could come up with a product. We're probably going to tweak it and then put it in later. And I think I'm going to try to release this code later into our repository so you can check your own release against the samples that we've had just to see how well you did it. But that's going to be the next one. But yeah, if there are any questions, that's sort of the end of the team line. And I think we have time for questions related to that.
let you use Markov chain instead of association rules.
So that was the part of the experimental design thing where I thought it would be fun. There were like that's one. That's also why you need to keep these experiments like pretty short. This one took me really 2 days to code up enough to get my but I played with Markov chains earlier, and I played the rest of the different projects. But this one I just give it a shot. All right, I think I'm going to turn it over to Phil now.
Just at
There you go.
Hey, I'm Phil Rock, and I'm going to be talking about malware. So some background on me. This is a picture of me at the South Pole, and that's because I worked on the ICQB students detector as a graduate student, got a PhD in physics. Built some machine learning models doing that. Then I changed directions and started forming images from radar data. Now I'm changing directions again and building those machine learning models for security. And I'm on the internet. So the problem is malware. And as you can see from my background, I don't have like an extensive background in malware or security, so you guys know why it's bad, or someone else will tell you why it's bad. That's at least true. And there's an opportunity. Right now, people use signatures. They use some scripts, some indicator to compromise to figure out what if a file is malware or not. But obfuscation can get around that sort of thing. Malware authors can use tools to just dodge simple rules and signatures that you write to try and catch them. But malware authors need to be reusing. Anybody who's written software knows that you can't just write a whole other program every time you want to launch an attack or get something done. So we hope to build a machine learning model that can exploit that code reuse and learn patterns from it. And we hope to get one that will just give you a thumbs up or thumbs down and say this is malware, this is not, and maybe even what kind of malware it is. But if we don't do that, the other possibility is that we can build a model that will provide some extra contextual information about the file that we find, and then we can present that to any investigator, and then hopefully that will be useful in figuring out what happened. This first half of the talk is going to be about some stuff I presented at another conference this summer called Sci-Fi. I also wrote a blog post. URL is right there. So I'm going to rehash a little bit of it and then give a little bit of an update on where we are on this. So this is a webpage from Kaggle.com. That is a website that hosts a lot of data science competitions. They give some data and ask you to learn on it and predict on some data where the answer is hidden. And one of those competitions, in one of them, Microsoft gave out a bunch of malware and asked you to build models around it. So here's some details about that competition. There were 10,000 malware samples released that had labels, 10,000 that did not, and you were asked to learn a model that would classify them into one of 9 classes. So I participated in it, I did okay, other people did much better. And those winning models, they used a bunch of different features, some of which were disassembly, byte engrams, compression ratios, and all kinds of other things. So during the competition, I was mostly focused on byte instruction engrams and learning how to use those features and what I can accomplish just using those. So first, a little bit of background on what those features are. Here, first I'll talk about byte engrams. And these are some images that try to motivate why byte engrams might be useful to a machine learning model that we might be able to do something with them. So these are some screenshots from a tool called BinBlad. The URL for that tool is here. So and this is some screenshots from some actual samples from that competition. When you open a file with it, on the left, there's a strip that shows kind of like file entropy as you go along in the file content. And you can see there's breaks in there. Those usually happen where file sections change change over. And so you can highlight what section you're interested in, and then on the right, you can see a 2D histogram of the byte treegrams. And so on the x-axis here, you have 256 values for the first byte. On the y-axis, you have 256 values for the next byte. And every time one follows another, that pixel is then moved up a little bit more. So in this example, I highlighted the text section, and you can see it lights up a bunch in the ASCII section, but also in some other places. And this is kind of a general pattern that you're going to see when you see executable code like x86 executable code. And then when you highlight that data section, you're going to see a totally different pattern, and a pretty distinctive one too. So the hope is that any machine learning model will be able to take this information and learn from it, and identify when a pattern like this occurs again, and then hopefully do something useful with that. So those are byte engrams. Instruction engrams are shown here. This is some text dumped from some files given out during competition. You were given the raw bytes during the competition with the key header script. And you were also given like some items, some output in IDAPRO. IDAPRO is a reverse engineering tool. And I think that program was run on some default options in a batch mode, and the text was just gone to some files and handed over to you. So then I did some, moved the data around and got all of the disassembled instructions all together like this. And then counted the occurrence of different instructions, and then also counted the occurrence of when, caller had appeared in that order, how many times that happened, and so on, with 3 and 4 things. And then use that information to feed the model. So going a little bit deeper in instruction engrams, like when the competition gave us that output from micro, like the first letter that in IDA is interactive. It's not really meant to be run distributed across a lot of different standards. So you can't really, like, I don't hope to run that over every example that we see in production or something. So early on, I really wanted to find some other solution to getting the disassembled instructions. I kind of turned to Capstone right away. That's kind of a framework an umbrella framework that includes a bunch of different disassemblers for all kinds of different platforms. It has a really nice and easy Python API that I was able to jump in and use right away, even as a non-expert in the field. And I got all that kind of disassembled instructions like I showed you on the slide. So I built a simple model based on the IDA instructions and one based on the Capstone instructions, like a similar machine learning pipeline with the same model that was used in the decision tree. And I got these performance numbers. These are cross-validation scores. And so the first score for the IDA would put you maybe in 100th place in the competition at like 300. The second score for Capstone would put you in like 200th place. But these are lower than I eventually finished just because I was limiting myself just to the disassembled instruction features. And so based on that, I was like, well, these IDA instructions are a lot better, and why is that? And so my conclusion this past summer was that the analysis passes that go into IDAPRO really give you a lot better data. They give you better features. IDA has a lot of proprietary analysis that you do when you feed it a binary, and so it's going to do a smarter job of disassembling than just if you feed the data to an off-the-shelf disassembler. So based on that conclusion that I had over the summer, and I was just kind of launched off and looked into all kinds of other binary analysis platforms, and I list a bunch here. I was really looking for some open source and distributable solution that would let me take a binary and just generate those instruction engrams, and that I could build a model on. So yeah, I looked at all these and tried to install them, tried to get good instruction engrams from them. But despite what Tim Hopper said, my skill set is getting open source tools and previews and what I read about on Twitter to work with the pipeline. Despite that, I still wasn't able to really do it. All those analysis platforms, they're all totally different. It's usually a huge challenge for me to just get them installed. And usually the idea of a lot of them, some of those is reverse engineering, kind of like IDA, in that they want you to be sitting there interactively working through the file and figuring out how to build it apart. So they're not exactly built to call a function to say, here's a binary, just give me all the disassembled instructions. So I came up with some crazy idea that I never really followed through on, and I'll kind of talk about why in the next couple slides, but maybe we should open source benchmarking tool that'll judge the analysis process and figure out how good some of these tools are at generating instruction text that models can learn from. We would include some data set of some well-known malware samples with good labels, and then just include a vanilla machine learning classification pipeline that would be automatically tuned and run, that could generate predictions based on just that kind of plain instruction, disassembled instruction text that I showed on the previous slide. And then I have like an area that you could just drop in code that would take a binary and generate that instruction text and feed it to that vanilla classification pipeline. So it's an idea. Ideas are cheap, they're worthless without execution, which isn't new. Part of the reason was I kind of dug into now why is capstone instructions doing a lot worse. And so this is the confusion matrix, and you can see it's evident. The model was really just confusing just two classes, and who knows how why it might have been doing that. You can look at those numbers and see that I was getting like 99% accuracy with the model based on HydroPro instructions, and maybe 98.6 on capstone. It seems like a small difference, but so that would matter a lot in production when you're really worried about the false positive rate. But maybe this is not something I really need to be optimizing right now. Yeah. So that's kind of the conclusion I came to. That really worrying about this would be premature optimization. This would be I don't really need to figure out exactly right now the best mapper of binary files to disassemble instructions. So yeah, that works kind of in tape. So yeah, now I'm going to give some random thoughts about building machine learning models and all. It's completely unsubstantiated before we get into the next part of the talk. But yeah, it kind of Endgame, applying machine learning to security. It's kind of different than what you hear about in other companies, where data science just comes in, there's an existing product, and you're kind of like trying to optimize ad click rates or get better performance out of your product, or really just increase your business metrics. Here, we're kind of trying to use data science to build a product to make something new, to solve some problem. And so in that case, I kind of thought it's not really worth it to just sit there and continually optimize a metric before we even have anything built or anything, or even build good data collected. So this is kind of how I see how the kind of flow of an eventual maybe malware classifier. First we need good data, then we can start building a model, kind of like I was talking about, and then we need to start delivering those predictions in some manner, maybe on a web front end or on an endpoint. And so kind of the work over the past few months has been that first step. Let's collect some good data, some data we trust, with labels we trust, and maybe we can mock up some really dumb delivery system for those predictions. And then once we have that, when we have metrics, then we can start really quickly iterating on those models. Yeah, so I've been diving into like data collection, a little bit of engineering, and I think that's not uncommon in the world of data science. I really think in large, it's really only in large organizations where you have already an engineering effort built up to collect the data and present it really easily to data scientists then data scientists really just focus on the model building. And I have some quotes here from some other data scientists that see that they're worried about the same thing. I mean, model building is really fun, so Dr. Wills has said that. So that's why he's worried about hiring data engineers to gather that good data set for himself. Sean Taylor at Facebook is probably running the same problem, and that's why he talked about why data scientists should probably end up collecting their own data. Yes, so one other thing on metrics, so here's a metric from some media article I came across while writing the talk, and some CTO says that his software was able to detect 20% more malware. So 20% more malware, that seems great, but to me that means nothing. And so when presenting metrics, like these are the kind of questions that I'm asking. And that I'm really asking myself when I'm building models. Like, I come up with some of those numbers and like not really believe them myself until these kind of questions are answered. And I guess I need to pick up two because I think they're really, really important. And that is the fourth one. What is your balance between detection and false positives? Like a number like that, or even a number that I gave when I showed this confusion matrices, it doesn't really matter. It doesn't matter what percentage of malware you detect. It matters what percentage you detect out of false positive rate. The false positive rate is really, you need to keep that super low for users to continue to use your product. Otherwise, they're just going to start ignoring too many alerts. I think we'll talk a little bit about that. And the fifth one, I think, is also very important. If you collect your data over 2 years of malware and then mix them all up, maybe pull 10% of that out in a test data set, and then train a model, you're going to do really well because you're going to see like the future iterations of that malware that you're testing on, and you're going to train on it, and you're going to know it really well. But the real measure is going to be if you make a time cutoff, build your model on all the malware that you've seen up to that time, and then test it and see how well it's going to do in the next week or two. I mean, that's the tougher problem. That's the problem we're trying to solve. How well do you do with classifying on malware that you haven't seen yet? And you're going to get two totally different answers when you do that. If you mix it all up in time, and if you rigorously make time cutoffs. So, of course, marketing exists, it's necessary. I'm just trying to encourage more skepticism about some numbers you might see. And also, I'm trying to say that there are really many barriers to sharing methods in this field. They already exist. There's IP. There's many risks to sharing your information in your models. So when we can share, let's make it valuable. Let's try and answer those 5 questions that matter. Maybe just have it. All right. So that's the end of the end thoughts. So the last part of the talk, I'm going to kind of walk through a blog post that my fellow data scientist at Endgame, Hiram, wrote. So what did he wrote a blog post kind of comparing 2 different ways of estimating Jacquard similarity between sets. And Jacquard similarity is shown here. That's the formula for it. What it is a metric to determine how similar 2 sets are. So why is this useful? Why am I talking about it in malware talk? Well, Hiram especially is very interested in nearest neighbor search and ways that you can use it. And it's one method to classify malware. If you get a new sample and you compare it to your data set where you actually have labels for all the samples that are in that data set, if you find 5 samples that are closest to this new sample and they're all the same malware family, well, then you can be pretty confident that that's the label that you should be predicting. So that's one method to go about malware classification. Yes? So, sure, no, good. You should slow it down. So, nearest neighbor search is one way to make a prediction about new malware samples that you might see. So, if you have a data set full of samples that have good labels, and then you come up with some metric how close your new sample is to every other malware sample that you have labeled. If you look at maybe the 5 or 10 that are closest to it, and they all share the same family, then you make a prediction. And nearest neighbor search, that there are, you can't do that. You can't make a distance metric from one sample to your whole entire data set. But there are existing algorithms out there that will shortcut that process, that will make some assumptions that allow you to get some distance to your family.
And
so what Hiram here is talking about is one of those distance measures.
yeah, and did you get better results with this?
Oh, the results will come. And we haven't yet compared it to, say, building decision tree or something. That was the method that won the hyper competition. It did really well there. There are 2 different approaches to the same problem, and we have yet to go into compare. So let's dive into these 2 methods of estimating Jacquard similarity. So min-hash was something I had no idea about a couple months ago, and reading the Wikipedia page did not help. This is hard. So I think my best tip to you guys is if you want to try this out, if you ever need to learn about min-hash, the best reference is finding massive data sets. It's a textbook that's available in PDF for free online right there. And here are some images that are ripped out of that textbook. So I'm not going to go into detail because, like I said, I'm only just now understanding min-hash, but I totally recommend going there if you want to totally understand it. But in general, you're taking a large matrix and you're a large matrix that has a bunch of different samples that you want to compare those to columns, and then you have a whole bunch of elements of those sets. And in the case of malware, that's going to be features that you come up with. In the case of Hiram's blog post, it's going to be strings. He just made some big data and generated some sets of strings. So especially when you're doing malware and extracting features, you can have lots and lots of features. So this matrix can be very large, and it's going to be really long and hard to compare columns to each other to find out how far apart they are. So the whole point of the thing is to get it down to some smaller size, where you get to choose the number of new features. So you get to choose how large this matrix is. In this case, you choose the number of hashes that you're dealing with. So now you're choosing the number of rows, and it makes it much easier to compare two columns together. The other method is bitwise, and it's talked about in this paper, bitthread. And again, it's the same sort of thing. You have samples under columns, and you have a lot of features in bitthread. Paper they talk about having 2 to the 128 features, which seems like a lot, even for a big engineering problem. But then they use a single hash function to map each of the rows into another smaller space of feature rows. Yeah, so there are two different methods to kind of reduce your data set. And here's a straight comparison of Hiram's blog post with the fake data that he had. He had 64 sets of strings and then 100, and then was reducing the data set down to 128 features. And then once you do that, you have columns. You want to compare the columns. You want to see how far apart these samples are. And then these are the two different equations that he used to do that. So how well did they do? Here's the results. Since it was fake data, since Hiram could control the size of the data and the computational feasibility, he made it so that he could estimate the real to part similarity between the two sets of strings. So he knew the truth, he knew ground truth, and then he knew these two estimates. And as you can see, min hash traces very well exactly what part similarity was. It was a very good estimate with larger variance. Bitthread always overestimated part similarity, but was also more consistent. So we call Bitthread a more biased estimator with smaller variance.
But its sample size was 64, right?
Yeah, I think the experiment was repeated a lot of times with different data.
But your data set was 64 unique strings.
I believe so, yeah.
You realize that this means that this test probably has no information.
What do you mean no information?
Probably it's insignificant.
Okay. But yeah, I mean, okay. Yeah, I'll
We'll pick up later.
yeah, no. I didn't think of that. And
know
I don't even know exactly. I thought the 64 was a different number of sets, but I'll go back to the blog post and see what Hiram did. That's probably a good one. So that was like how well these two methods estimated that distance metric. So now when we moved on to the problem of nearest neighbor search and said, okay, now that we have these estimates, how well does it do an actual nearest neighbor search? And in this case, we're looking at, we know the real neighborhood of each sample from the real data. And so now we're just looking at the distance metric and seeing the neighborhood given by returned by the distance metric and comparing that neighborhood to the real actual neighborhood across different neighborhood sizes. And you can see Bitthread's smaller variance allows it to have greater recall. Recall is to do the two neighborhoods match. So in this case, again, this was the toy data set. This was a simulation. It did really well in small neighborhoods in just comparing distance from what was close to each sample. So now we moved to the actual application. We ran this on real features from real malware, and we generated TC plots. And TC is kind of a projection that takes something from a large dimensional feature space and projects it down into 2D. But the point of the algorithm is it tries to maintain the same distance between each sample that exists in the larger feature space in this 2D feature space. So, and again, in this case, that distance is measured by the min hash estimate or the bit shred estimate of the card somewhere. So here we're actually testing how well the estimate did from each sample to every other sample, not just the neighborhood. And there were some pluses and minuses to each of them. You see min hash had tighter. What this 2D projection probably shows is that there's more separation between families, which means a machine learning model will be better able to pick out different families and make better predictions. But when we moved to bit shred, it did a lot better with like the red groups, like there's 3 different red groups kind of distributed around the min hash. Here, bit shred has brought them together, so for one family it might do better. 3 other colors that a machine learning model trained on this data would probably be able to draw boundaries between. But here, in this estimate, bit shred, those kind of colors get all mixed up. So yeah, that's the results of the experiment. We're still looking at them. We're still kind of learning how good each of them are. And that's it. I have no conclusion for it. So, yeah.
What was the reasoning? Why did you think that changing the measurement function might yield better prediction? Was there a mathematical condition like that?
I don't mind telling you if there was a justification for why I was looking at it. I think he's more familiar with min hash, so he wanted to see if the method presented in the bit shred paper was better or worse, or maybe faster or slower. I'm not sure.
No,
in the blog post, he doesn't get into how quickly each of those can be calculated. So that's another consideration.
I think this pertains to the Jack similarity measure.
Okay.
More,
like an alternative to that.
yeah, alternative.
We haven't thought. Yeah. So like this, right, uses one hash function, maybe compare different hashing techniques in that. No. Okay. Okay. Cool. Yeah. No, I don't think we thought.
Was your conclusion about IPRO versus the others? Was the IPRO fast enough? The others just didn't find? Or did you not?
Well, so there's only one other that I have to work with, which is Capstone. This takes a single pass, it's fed by data and gives you this assembly back. No, when I build models based on the IPRO output, I mean, I got better results. So yeah, I thought that it has smarter analysis packages with better determining divisions between functions and subroutines and things like that. But I could be wrong.
So you were assuming it found stuff with it.
Yes. In the first set, the first half of the talk was the malware. Microsoft released those knowledge samples, and so they had the PE header script. So it's kind of like you couldn't do everything you might want to do with all the samples. But in the second half of the talk, at the end there, I think we did run that on half the sample. I know in the Microsoft, no, there were in the competition. I think there were some packed. You could look at the entropy of some of those samples and see that they were packed. And there's probably some packed samples in the set that Hiram used for the blog post, but I'm not sure about that. I must be there. Okay, thanks. Yeah.
Oh man, the joke ruined. It's not funny anyway. So whatever. All right, guys. My name is Andrew Morris. My talk is on sonification of real-time port scan data. So again, my name is Andrew Morris. I am an analyst at Endgame. I'm insanely less qualified to be talking to you guys than the previous three speakers who all have PhDs and master's degrees. I dropped out of high school. I have a background in penetration testing, red teaming, operations, office operations, and I love puns and beer. So kind of background, let's talk a little bit. What does that stuff mean? Raise your hand if you've ever heard of like mass scanning. Great, oh, thank God. All right, so that's gonna make this talk a lot better. I've given this a similar talk, no one had any idea what it was. I was like, this is gonna be awkward. So internet-wide scanning, internet-wide mass scanning is very commonplace in 2015. The internet is very noisy in 2015. Everyone is like mass scanning the crap out of the internet all the time because there's tools like mass scan and CMAP and like unicorn scan, and all this crazy stuff that make it like actually really easy to scan the whole IPv4 space. There are literally billions of packets just like flying in every direction around the internet. And there's so much of it that it's really hard to distinguish like, I guess, malicious and benign and internet-wide and targeted traffic and all that stuff. It makes it really, really hard. So at Endgame, we built a system called SensorNet that basically takes all of that and categorizes it in a certain way. And today we're going to talk about how we use it to make music that sounds horrible. So again, sonification is the production of sound, making sound from something, right? And then a port scan, raise your hand if you know what a port scan is. Thank God. All right, so port scan, as we all know, is like connecting like on the network, trying to connect to a service, and then basically just looking to see if that service is open or not to figure out what services are on a machine or something like that, right? So how are we going to make music from the background noise of the internet? How are we going to listen to the internet? Well, the first thing that we're going to have to do is we're going to have to build something that gauges and like measures all of this background noise and like collects it, right? So let's talk about mass scanning a little bit, like what it is, why people do it, stuff like that. So mass scanning is sending some type of request in every single direction on the entire IPv4 space. So that means all 4 billion IP addresses in the IPv4 space. 1.000 to 255.255.255.255. That's a lot. That's a really big number. When you actually do it, it looks like this. When you use the tool, it's like you execute mass scan on 0.000/0, which is like the funniest subnet mask ever. And there are good and evil reasons to do it, right? Just like kind of everything ever. You can like find every machine running a certain piece of software on the internet. You can categorize all the different web pages on the internet. Find every machine running a certain operating system. There's a ton of different use cases for why you would do it. Search engines do it, right? Like Google's been doing this for years. It's what they do. They crawl the whole internet, pull like a little bit of website information, just enough to like index it, put it in a database, and then when you go to search Google, all you're doing is just asking them about the data. Like, yo, tell me about this thing, right? Baidu, the Chinese search engine does it, DuckDuckGo, like all of those things. Security researchers all do it. Have you ever, raise your hand if you've ever heard of Shodan? Okay, great. So Shodan does this for you. Scans.io is something I think run by the University of Michigan, or maybe just a, actually, I don't know who runs it. So it's, yes, now it's, well, since it's like reads from scans.io data, but I think they're the same person. I think they're the same group, rather. And then there's like malware that does it, right? If you have a worm that wants to spread to lots of different computers, it's going to try to hit as many different computers as possible, right? And opportunistic bad guys, like bad guys that are literally just trying to compromise as many different computers as humanly possible for whatever reason. So if you ever want to like see the background noise of the internet for yourself, you can just spin up like an AWS host or like a DigitalOcean host that's like sitting right on the internet, and you can just turn off all the firewalls and turn on TCP dump and just watch it. And you'll see traffic after a few minutes or whatever. And that's like the traffic that's just flying around the internet, and everyone's just like, oh, okay, whatever, sounds good. So if you're in incident response, this like mass scanning stuff can actually be really inconvenient. Raise your hand if you've ever done any incident response before. Okay, great. So, you're doing instant response on something like maybe a web server, it's compromised. And this is you, you're like, oh, just doing some instant response, right? Having a great day, looking at some logs. Oh, yes, of course, there's some logs. That's very, very interesting. Oh, Jesus, there's just so many logs. God, they're just, please stop. There's so many logs, just logs everywhere. And you're just like, you're just like, please kill me. And so if only there was some way to differentiate between internet-wide requests that are being pointed in every single direction and just targeted traffic that's just hitting you. There's like no way to do that right now. Except, we built something to do it, and it's called SensorNet, and it's pretty cool. And we're basically trying to solve that problem, right? How do I tell if something is pointed in every single direction, or if a piece of traffic is just coming to me, right? So the way we build, basically, at a high level, SensorNet is a large amount of servers that sits in a ton of different places, like lots of different data centers, lots of different countries, and it's geographically spread, so different countries. It's logically spread, so different areas of the internet, right, like different subnets, crap like that. Centrally managed, everything like talks to a centralized place where we can query stuff, and it's untrusted infrastructure, so we don't care what happens to it. We'll just mute it, and it just like shifts around all the time. It's great. And we gather a lot of data. We can kind of think of it like honeypots, but it's not really honeypots. It's just supposed to sit there and collect background noise. That's all it's supposed to do. Right now we've got it, getting HTTP data, SSH authentication data, and whatever else we want. It's really easy for us to add new stuff to it. If we want to see like data type of data, we can push out some infrastructure that puts that in it. And we get a lot of IP table stuff. It's a horrible screenshot. A lot of like telnet stuff, like credentials that people are using in their teams, where they're coming from. POF is passive operating system fingerprinting. It like examines the TCP, like all the flags that are set in a TCP packet to like basically make a guess, like, oh yeah, that looks like Solaris because Solaris has a TTY of this or whatever. So I was talking about this before, like why did we actually build SensorNet? It wasn't just make horrible music. We wanted to figure out, am I the only one, answer that question, am I the only one seeing this traffic? Is this a targeted attack that's coming, or is this packet, or is this request like targeted to me specifically, my organization, or is it everywhere? Is CVE blah, 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 blah actually being exploited? Is anyone actually exploiting it in the wild? Can I just like hide all of the traffic, all of the logs that's like in everywhere? Can I just like not see that? Because I don't want to hear about that. I only want to hear about stuff that's somebody targeted from a security perspective. And where are all these attacks coming from? And we can answer all those questions, right? SensorNet data, like in Endgame, SensorNet actually feeds into other internal products that we use to help us make better decisions with regards to threat intelligence, IP reputation, and some like malware capture stuff. So it kind of looks like this. Basically, we have traffic, like a thing will happen, which will go to a service, which will write to a log, which will get forwarded to a message queue, which will get dumped to a different place, like or streamed or consumed by somebody, or like dumped into a database that we have an API that can query. So like you can ask that question, like have we ever seen this IP address before? And SensorNet can be like, yep, you've seen it, you saw it on this day for the first time, this day for the most recently, and you've seen it this many times, or whatever. The architecture was kind of like this. It's actually not banged on this background of it. So basically, like there's these sensor nodes, which are just a bunch of servers. You got scan traffic that's generated by bad guys, search engines, and worms. You've got your engineers are scanning these things up. It writes all that data to a message queue, which is consumed by lots of different types of consumers, right? Take the screen, so he's going to go build it. The tech stack that we actually use kind of looks like this. For the infrastructure deployment, we use Terraform, which is a HashiCorp thing. It's really, really cool. Basically, it makes it really easy to deploy infrastructure in like a provider agnostic way. You can basically just say, hey, I want a server, and I want it on DigitalOcean. And it's like, okay. And so it's like basically something that sits in between you and the APIs that you want to talk to, so servers and whatnot. We use Docker for the sensor applications. Docker for the sensor applications themselves, because just for portability reasons. We use RabbitMQ because it makes complex wrapping stuff easy. And for the sensors themselves, we use basically like zero interaction honeypot sort of things, like things that do literally nothing, and that just sit there and just catch logs that are coming in. We have some custom sensors that we've written. Threshing floor is one of them. We will, I think, be open sourcing that soon. It's a HTTP honeypot, sort of. All it does is it's a web server that delivers back responses based on what you ask for. So if like, a bad guy asks for, like, requests a WordPress login page, it will give it the response that it's looking for just enough so that an automated scanner or something will send the payload or will send credentials or whatever, something like that. We have basically templates, signatures for it we use to basically coax additional information out of that. And we used MongoDB to write stuff to it. So some of the problems that we've encountered, how do I spin up several hundred servers? I talked about that a little bit. Terraform was great. How do we run different services on potentially different build environments? Docker, fantastic. How do we work? So one of the problems initially is like, it was gathering a tremendous amount of data and we were keeping it compressed. And when I was like trying to work on like a compressed data set, I'm like, oh, Jesus, like, how do I like, I don't want to uncompress this because it's going to fill my hard drive. So like stuff like that, working with compressed data. I'm not a data scientist, so I do this like the most horrible way possible. How do we move logs instantly from wherever they're getting written to a message queue? We wrote a custom log forwarder that basically just sits there and watches a file, and whenever the file has a new line, it zaps that new line to a message queue that we have set up. And then we basically, like, this is kind of fancy. We have our log forwarder derives all of the information that it wants itself. So our nodes figure out what country they're in, what provider they're on, like what their IP address is, what service it is, what version it's running. So they figured all that out itself, so we don't have to teach it. Like we don't have to config, like have a config file or something like that. It figures it out based on a number of different ways. So some of the metrics that we have collected, the amount of nodes, like the volume that we have is kind of constantly shifting, but at any given time, 100 and 1,000 servers on there. These metrics are actually like, I'm gonna have to go back. Don't quote me on any of these because this is like as we're building the thing right now. So sometimes stuff is up and down. Average, we generate 200 to 300 gigabytes of compressed logs per day, which is like 2 gigs roughly of plain text logs. We process 2 million messages per day from all the services. That fluctuates. It depends on what people are doing at the time. It's really the norm. And on any given day, I would say, as a norm, any given sensor that we see gets about 500 to 1,000 totally opportunistic connections to it per day. That's like average. And then there's, when a new bug comes out that's on a certain port, that's going to increase, stuff like that. And we actually see a lot more traffic if the server that we put up has been indexed by Shodan or Census, which basically means bad guys are pulling their data from Shodan instead of just scanning for it, which totally makes sense. So in October of 2015, the top ports that we saw was pretty much exactly what you would think it looked like. HTTP was the top. There was some weird stuff, but I had to discount it. Like there were some people that were scanning really hard for like Bitcoin mining software, like trying to steal cycles from people. And there's like weird stuff that happens every now and then. One of the problems you'll run into when you stand up a server on the internet, or when you stand up a lot of servers, is sometimes you'll stand up a server that takes an IP address that belongs to someone else 5 minutes ago, and they're still trying to request resources on that server, or you still have like a stale DNS pointer that's pointing to you, and all of a sudden you're getting all their traffic, and you're like, oh Jesus, like what is happening? So we had to actually like, get rid of all of that. Whenever that happens, we have to nix that out of our data set because it's not normal, it's like different. UDP, TCP stuff is pretty much exactly what you think it would look like. And then the more interesting stuff is actually the stuff that's at the bottom of it, like what's very rarely scanned for, but still scanned for. UDP, usual suspects, basically the top 5 most common services. Not really any surprises right there. Weird stuff, like I was saying before, like a lot of people scan for Bitcoin miners to like try to connect to them, mine Bitcoin with your CPU cycles and stuff like that. Still a lot of people exploiting shell shock. A ton of people looking for unauthenticated HTTP proxies. A lot of people using default creds for like embedded devices, routers, like Tomcat installations, JMX console stuff. A lot of worms trying to just propagate themselves. The stuff that you basically expect would be there. So to just like kind of go over a little bit of what we've done for Cincinnati, what we've talked about now. we gathered a ton of different data by deploying all these servers that are just catching logs and catching events that are just happening everywhere on the internet. And we are aggregating all of this information centrally with a custom log forwarder that zaps logs to our centralized place as soon as it happens. We're archiving it in the database. Well, we're archiving it in the cloud, putting it in a database so we can access it, and we're querying it with APIs that talk to that our other internal services are asking, like, hey, have we ever seen this before, or whatever. And some of the things that we can discover from this is, like, we can see everyone who has ever mass scanned the internet, like, starting from when we built the system. So if you have ever run mass scan from, like, home or from anywhere, we have a lot, right? And so does everyone else, but we like to keep all of it, right? Everyone that does things on the direction. Who are the usual suspects? Like, where are the usual suspects? Everyone talks about, like, should and having census and stuff. We know where they are. We know where all of their servers. What are all the ports that people are scanning for? We talked about that earlier. What is the normal amount of scan traffic? Like, what you need to have that question answered if you want to figure out if you're getting undue attention, not if you're being targeted, if somebody's attacking the website. You have to know what the normal amount is if there's just, like, all of them that's happening. What tools are people using for masking? We can figure out a lot of that stuff from some of the, like, TCP fingerprinting and stuff like that. What machines are compromised? That's actually kind of cool because we can see based on a lot of the times it's not bad guys that are scanning the internet, it's just a compromised computer that's scanning the internet. And we can use a number of different metrics to figure out what is compromised and what is what's, like, a bad guy actually doing bad things. So without further ado, where is the that's right here. I'm going to present to you the most inefficient musical instrument in the history of mankind. We are going to sonify port scan data by, I'm going to sonify port scan data by having something that subscribes to all the port scan data and converts the port numbers, which is a number from 1 to 65,535, 36, whatever, to piano keys. Rich actually came up with this process, which is really cool, by basically just dividing the number by 88, which is the amount of keys on the piano, and then using the remainder as what actual note it plays. It sounds awful. And then the volume is actually determined by the literal distance away from, like, the TTL, which is the time to live, which is decremented every time it passes from one hop to another. And it's going to stream all this to radio.endgame.com. So let's see. Oh God, I really hope there's nothing horrible. Okay, all right. Oh yeah. Oh yeah. Oh Jesus, sorry. What am I doing? The internet's kind of quiet right now. There we go. There it is. There we go. So you got that, right? Listening to the actual background noise of the internet, it sounds just as horrible as you think it sounds. But what's, I guess, even cooler than that is, oh geez. This is the worst thing. I have to use PowerPoint. Right, okay, so let's actually go a little bit further and let's write a custom network scanner that plays actual songs. Because why the hell not? Why wouldn't we do that? With Endgame in script, so I'm going to give you an even more absurd demo than the one I just gave you. Let's see if this will work. Alright, I give you, let's see, here's Heart and Soul. Alright, we've done that with Endgame. Now, for the grand finale, I give you solo. That's it. So that is Endgame Radio. Thank you. Thank you very much. I don't know how to just jump to one slide.
Shift F5.
Shift F5? Thank you. Godsend. Thank you. Oh, geez, what have I done? All right. Does anyone have any questions on this? Yes?
Are you worried about having, if somebody were to be able to maybe track down a lot of SensorNet was able to track down maybe a lot of them, maybe a couple days before they were going to launch the track company, the customers with poisoning the data and like background data. Like, I guess, how are you trying to actually, distinguish between like somebody who's trying to actually target you and poison your data versus background?
Okay, the question is, how do we handle somebody trying to poison our data by, I guess, introducing new scan traffic to maybe look like everyone else and then doing a targeted attack? How are we protecting our customers from that? That's a great question. That's actually a question that's a little bit more mature than like we have gotten to the point of. There's certain things that we do to prevent fingerprinting our infrastructure. Like one thing is like you pretty regularly tear down and put stuff up, and just the actual specifics of how we have built things, it's actually kind of difficult. Even if I already give you the IP addresses of like 3 of our sensors for whatever reason, it would still be really hard for you to figure out where they all are because there's so little information to fingerprint them. So it's actually very difficult to do. Aside from that, not really a ton. Like if you knew where all of them were and you knew who was consuming the data, you could probably trick like a victim into thinking that something is everywhere. But both of those things are actually very hard to do. If that makes any sense. Does that answer your question?
Yeah.
Great. Any other questions? Yes?
Thought about making this your hold music yet?
Have I thought about making this my
Hold music.
hold music? It just sounds so bad. But the thing is, and Andrew was talking about this the other day, actually, we were talking about it. Sometimes I'll like leave it on without really realizing it. And it's like background, it's like white noise, and you don't really realize it until you've been sitting there for like an hour and it's been on the whole time. You're like, what is wrong with me? But yeah, we don't really have. If we had a great phone, we should totally. That's actually great. Oh, like the actual. I guess I should know the history of sonification. Okay, yeah. So I should have gone into the history of sonification a little bit. There used to be a tool called Snoop on Solaris back in the day. I just learned about this today. Just kidding, I know everything. And there was a tool on Solaris, it was a network sniffer, but there was a -A option in Snoop where you could like literally listen to the traffic. Like, you would actually pass the traffic to like /dev/audio or whatever, and actually like literally hear it. And that also sounded terrible. So. Any other questions? Yes? Great question. The question is, how do we filter out leftover traffic from stale DNS that's still pointing to our thing? So there's a number of different ways you can do it. One is just like if you have a server that's getting 20,000 requests per second or like per hour, and you're used to getting like 500, you immediately know like, all right, bad news bears, bad data, get rid of this thing, right? One of the things that you can actually do, this is kind of crafty, is you can have if you're using sort of our architecture, one of the things that we do is we have a consumer, a specific consumer that consumes HTTP data. And what it does is it looks at the host, the request, an HTTP request has a host parameter, right, which is telling you what the host name is that it's looking for. We'll have a consumer that will look at that for all machines, and it'll say like, oh, this thing has a host parameter of this IP address. Let's resolve that IP address and see if it points to one of our resources. If it does, automatically tear it down and put it in the wall. Does that make sense? Okay, yeah, so like basically just a separate consumer that's looking at our data, and if we get a request that has a DNS thing, like a DNS entry in the host parameter of the HTTP request, it just says like, is this pointing to us? All right, like this is bad, let's kill this thing, stand up somewhere else, get another IP. There's also a lot of really crazy implications with scale DNS, but that's a talk for another day. Any other questions? No? Oh, yes. how does this work for our users? So one of what is the value our users take away from? What do we do with our users? For them, so I guess I'll only talk with capacity to what I just talked about, just to try to specifically answer that question. Basically, with this thing, it's trying to answer the question of like when people are looking at all of their logs and a particular request or a particular IP address that they're investigating during incident response or during a hunt or during anything like that, just figuring out definitively whether or not a request was targeted to them or omnidirectional across the entire internet. Yeah, that's certainly one reason, yeah. But also just to basically give a little bit of insight into severity, right? If you have like a router on your network and it gets compromised, that could either be a really, really big deal or not really that big of a deal at all. If it's compromised by like a worm and nobody really that's being seen everywhere, that's not as big of a deal. But if it's compromised by somebody that we've never seen in SensorNet, that's a little bit of a bigger deal. Because you know that was at least somewhat targeted, right? Does that make sense? Great. All right. Does anyone have any other questions? No? All right. Thank you guys so much. My name's Andrew. Thanks to the other speakers. This is all of our information. If you have any questions about any of the stuff that we talked about today, either hit us up on the Twitters or email or anything like that. So, what? I don't know what you're saying.
If any of you guys want to hang around, we are actually going over to the Village, which is called Folsom. We have a little bit of a space reserved, so people step by and have another beer and hang out. We'd love to see you.
Free booze. All right, thanks everybody.
Hey, so thanks for coming out to this meetup. So thanks to Endgame for coming out to this and hosting this at Parisoma, and thanks to Parisoma for having us here as well. The next meetup is probably going to be in January. I don't have anything planned for December yet, but if you have like connections or anyone who you think would be interested to give a talk, then reach out to me and Clarence. Thanks for coming. And thanks for our gamers at home too. So I'm sorry for different YouTube accounts at certain point between this. The videos will be online, so you're gonna, yeah.
I told Seymour that I would say hi. Yeah.
Bye.